Hello everybody, we are now in week 7 of this particular course. We shall begin sequential logic circuit from today's class, and we shall have a quick recap of week 6. I believe it was a little bit heavy because that was the last week of the combinatorial circuit discussion, so a lot of advanced things were there. So I hope you could assimilate them. But as we had done in case of combinatorial circuit, we made a soft start with introduction of basic gates and all, then we moved on to build more complex circuit. So similarly, we shall start softly with basic components of this sequential logic circuit, by which we shall make more complex circuit in the later classes. Okay. So we discussed a magnitude comparison of two numbers and how outputs like x greater than y, x is equal to y, x less than y were generated, and in that case we had two kind of approach. One is of course by subtraction, and another is by comparing the more significant bits of two numbers successively. Okay. And then we discussed arithmetic logic unit, and we saw that one device which is versatile in nature, depending on the selection unit, it does perform one of the many different arithmetic or logic function. And we saw that how all these devices can be cascaded and more number of bits can be handled together. Then we discussed unweighted codes. Okay, and then we saw that how gray code is advantageous where two consecutive number change by only one bit position, and we also discussed XS3 code where we saw that the BCD arithmetic, the way we had conducted before, that can be made simpler by XS3. And then we looked at error correction and error detection codes, and in that context we defined Hamming distance, and we saw that minimum Hamming distance in a particular coding paradigm, how that can be useful in deciding or in understanding how many bits can be corrected or how many bits can be detected. Okay. So, in that context we discussed parity code, standard parity code, even parity, odd parity code, which we discussed in one of the earlier weeks, and also we discussed a new code, Hamming code, which can detect two error and correct one error in bit position. Okay. So, this was in brief what we discussed in the and of course, yes, we discussed multiplication and division, right, and we saw a bit seemingly complex circuit, but we had examples by which we could appreciate how the processing was done through the array based structure in the unit cells, and finally the results were obtained. Okay. So, each of the cases we have defined the unit cell properly and looked at the solution by taking specific examples. Okay. So, with this we start this week's discussion. As I said, we shall start with defining basic units of sequential logic circuit, which is memory element, also called flip-flop. But before that we shall see what is a bistable circuit. So, bistable circuit is something where the circuit is stable in one of the two positions. Bi stands for 2, right. So, both the positions are stable, right. So, if you look at this a switch where you are applying a specific force by hand and all, and then you are connecting the switch to this particular place, then you remove that hand pressure or this whatever force, external force, the switch will remain in that position till you again put a force and bring it here, again it will remain there if you do not force it to go to another position. So, each of these state is stable. Okay. So, in bistable circuit we can store one bit of information, that is whether it is output is high VCC or output is 0, right. So, together you can store in the context of binary representation of information 1 bit information we can store in a bistable circuit. Okay. Now, moving over to digital circuits. So, let us see if we have two inverters connected one after another, right, and we place a 0 volt here. What will happen to it, to the inverter outputs in these cases? The first will be this 0 volt, it will be 5 volt, right. So, logic 0 will become logic 1 here, and again it gets inverted, it is logic 0. Okay, this is understood. Now, while this ground is there, you connect a feedback. So, this feedback is key. This feedback is very important in developing the basic cell and the sequential logic circuit, right. In the combinatorial circuit, we didn't include feedback. So, the feedback comes in the sequential logic circuit discussion. So, you connect a feedback the way you have seen from output to the input, right. There is no issue, no ambiguity, because this is 0 volt and this is also 0 volt. So, this is logic 0, this is also logic 0, this is logic 1. Now, if you remove this ground, like the circuit becomes like this, what will happen to the circuit? It will remain at this 0 volt, this 0 volt here is driving this one, and this 0 volt is driving this 5 volt is 0 volt. So, it will remain in that place like as a stable formation, right. This output will be 0 volt. Now, instead of this ground, if you had started with a 5 volt here, then a feedback, okay, and then you remove that 5 volt, what would have been the output in this case? The output would have been stable 5 volt. Okay. So, this is what we can see a bistable circuit in the context of digital logic representation, right. But what we find here, that this way of applying external this ground or 5 volt, this is a bit inconvenient. So, we would look for something which is more convenient to trigger from one particular state to another. So, towards that, let us look at this circuit where we are having, instead of NOT gate, we are having 2 NOT gate. Okay. So, you can see the feedback happening here, and we can draw the same diagram in a different manner, which is a bit cross coupled, okay. But there is one feedback, you remember, and one is in the forward path, but this is the way you can draw it, okay. And we give these inputs some name S and R, and more about that it will be clear very soon, okay. And this is Q, and we will see that it happens to be the cases where we are operating it, the way we operate it, this V3 will be inverse of V2. So, if this is 0 volt, it will be 5 volt and vice versa. So, that way we can write it to be Q bar, okay. But we shall see more of it in the subsequent discussion, right. So, consider that both of them are 0 0 at a given time, okay. So, for a NOR gate, 0 is a non-forcing input, okay. For OR and NOT, 1 is the forcing input. For OR gate, if 1 is there, output will be 1 irrespective of what is there in the other input. And for NOR gate, if 1 is there, output will be 0 irrespective of what is there in the other input, isn't it? So, these are forcing input, right. So, 0 0 is non-enforcing input. So, it will look at what are the other inputs by which the output will be decided. So, if to start with you consider that this was 0, right. So, then this 0 0, this is 1, right, and this 1, right, is making it 0. So, this 0 and 1, if the previous value was 0, right, then it will be 1, and from the symmetry you can say if this was 1, this would have been 0. So, if you look at this truth table, this is what you can see, that 0 0, then 0 0 and 1 1. So, whatever had made the previous value 0 or 1, that will be continued with when these two are 0. So, the prior value of Q, it is latched into, okay. This prior value of Q is latched into, right. Is it okay? So, this is what we see when 0 0 is present. Now, let us see if you present a 0 here and a 1 here, Okay. So, 1 is a forcing input irrespective of whatever was the past value or so, because this is coming from an external. So, this will make it 0, right, and this 0 0 will make it 1 even if the previous value was 0 or 1 or whatever. So, ultimately this 1 forces it to be 0. So, when this is 0 1, right, S is 0 and R is 1, irrespective of what is the previous value, the output is always 0, right. And similarly, again from symmetry, if this is 1 and this is 0, this is the case, right. This 1 will force it to be 0, this 0 0, this is 1, so output will be 1, right, Q will be 1. So, this is what you can see. Is it all right? So, if it was set, this now S stands for set and R stands for reset. So, when S is 1 and R is 0, we say this particular latch, this is basically, it is called latch because it is latching whenever we are putting a 0 0 value. So, whatever the past value which made the Q 0 or 1 because of 0 1 or 1 1 1 0 that was present, it latches onto the past stage, past value, past state. So, that is why it is called latch. So, this S stands for set and R stands for reset. So, 1 0 is setting of the latch and 1 0 of S and R, and 0 1 of S and R is resetting of the latch. Okay. Is it fine? Now, what would have happened if 1 1 was presented here? So, the output would have been 0 0, which is fine. I mean, as such there is nothing, no ambiguity about it. But after 1 1, if you try to put into that resting state when the past value would be latched onto, so after that if you put 0 0, then what happens actually, that this 0 and this is external 0. So, both are now non-enforcing, right, and this 0 is over here. Now, depends, I mean, which one of them gets the 1 before the other. Ideally, one can say that both of them will get 1 together. So, that 1 will go to the feedback to the respective cases. So, both of them will become 0. Okay. So, that is the ideal case, but actually where the propagation delays are identical, but whatever be the fabrication process or so, you will see that one of them, okay, which is not for sure because of the way it gets fabricated, the different transistors and other things are there in the circuit element, passive element. So, one of them will be having a higher propagation delay than the other. So, that will respond slower, which we cannot say as a designer which one is going to acquire the one value before the other, right. So, that is something which becomes a bit unpredictable, and a race between these two who wins, and that is something which we would like to avoid in a SR latch use or application. Okay. So, that is why this 1 1 we are saying as not allowed. Clear? So, how do we again we will look into the the representation part. So, we will not write all those basic gates that we have used. Instead, we can prefer to put it in the form of a symbol, which will help us in making bigger circuits. Okay. Otherwise, the circuit will become a bit clumsy, too many logic gates and all. So, when we say SR latch, so this is the way we can put it, and if you look at the textbook, two different symbols have been used. In one case, Q and Q bar are put inside. In both the cases, we will see SR is there. Okay. And that means this is Q and this is the invert of it. That is what we have seen in the cases, the allowable cases, right. And in another representation, Q and Q bar is kept outside, but now there is an inverter, a bubble that is a not operation, that opposite operation that is being shown here. So, that means whatever is the value here, it is opposite here. Okay. So, these are the two conventions you will find in the textbook. Okay. So, now we can whatever truth table we had seen before, now we can put it in a more compact form, since we are trying to come up with a compact representation. So 0 0, so previous value is written, okay, previous state is written, 0 1 of S and R, output is 0, 1 0, output is 1, okay, state becomes 1, and 1 1 is not allowed. So we had seen the way the NOR latch works. So if we had connected NAND gates in the same manner, right? So what would have been the corresponding truth table, okay? So in the NAND latch, if you look at it, so NAND for AND and NAND, what is the forcing input? 0 is the forcing input, okay? So if AND gate 0 is there, then irrespective of the other input, the output will always be 0. And for NAND gate, if 0 is there, output will be 1 irrespective of the other input, okay? So in this case, if you just look at this particular block, okay, so you will see that if this we are giving it a name S bar and R bar, because that is the way we will see that relationship with this particular table, the previous NOR latch. So if both of them are 0 0, right, so the output will become 1 1, right, and if both of them are 1 1, right, then it is non-enforcing input. So it depends on the previous value. So if the previous value was say 0 and this was 1, so 0 and 1, this will be 1, and 1 1, it will be 0. So previous value will be returned, and previous value was 1 and 0, so this will go to 1, and 0 1 1, it will become this 0, it will go to 0, and this will become 1, and 1 will come over here, and 1 1, it will become 0, okay, the other case, right? Or you can see it from symmetry also, right? So this 1 1 is your previous state, right? Similarly, you can see 1 0 will be, output will be 0, 0 1 will be 1, and 0 0 it is 1 1 because is forbidden because after that if 1 1 follows, output becomes unpredictable and depends on the race between this gate and this gate, okay. Now if we are looking for a SR latch made out of this, and we want a truth table like this, so what we need to do? We need to put a NOT gate before it, isn't it? So a NOT gate before it, and this NOT gate you can get by a NAND gate also by joining the two inputs, right? So this S bar becomes S here, and R bar becomes R here, clear? So you can use IC 7400, which has got which is quad 2 input NAND gate, to realize this one, okay, fine. So this is one IC where within it the SR latch is already made, okay. So this particular IC, if you see, there are 4 such latch, 1, IC 74279, 2, 3 and 4. So 1 and 2 is normal SR latch, okay. Since it is made of NAND, so you can appreciate that the input will be S1 bar, it is given a name S1 and R bar, okay. And in the other case, you have got 2 inputs, S1 bar and S2 bar. So this is a 3 input NAND gate, and this is R bar. So for the other gate, you have got only 1 input, and for that we shall have a truth table something like this. How? Okay. So we can see that if this particular case, all of them are 0, this is forbidden, okay, because then the output will become 1, right? And then if S1 is 0, then this output is 1, this output is 1, right, irrespective of S2 is 0 or not, because one of the forcing input has become 0 for NAND gate. And at that time, if R bar is 1, so this R bar is 1, right, just by considering the way we had considered it before, we can see that this is 1, this R bar is 1, so 1 1, it is 0, and 0 is fed back here, it is 1. So the output is 1. Similarly, from symmetry, if S2 was 0 and irrespective of S1, the output will be 1. And when both of them are 1, right, that means this is non-enforcing. and R bar is 0, okay, then the output becomes 0, right. And when all of them are 1, the output is in the last state. Okay. So, this is what we can see for IC 74279, where the latch is already there inside the IC. You do not need external connection using NAND gates. Now, one application of, there will be many applications we shall see later, and complex sequential logic circuit will be made. So, right now we can see one application where a Debounce switch can be made using SR latch. Okay. So, what do we mean by Debounce switch? So, when we are basically connecting a mechanical switch which is kind of having a spring load kind of thing. So, whenever it is getting connected here, right. So, it will make a connection, disconnection, connection, disconnection, connection, and then it will settle. So, there will be a small vibration, right. So, and when it disengages from here, this is the output that we are talking about here. When it disengages, when it is connecting here, it is making an oscillation, but it is connected to 0. So, it does not make any difference here. So, only when it is getting connected at this place, getting closed, at that time there is a small vibration because of the spring action that is there. So, you will see that whenever it is getting closed, for example here, so there is a small vibration taking place, high low, getting disengaged, getting engaged, right. Right, and when it is getting open and connecting to this place, so it is immediate, so there is no such issue, again it is getting here. So, where ideal case we want this, but actually this is what is happening, clear. So, this ringing can create issues, because it might say that number of zeros, ones have come into the picture, so which might create difficulty. So, it can trigger many events. When actually one event has taken place, one such closure has taken place, it may count that 1, 2, 3 such closure has taken place, and each closure might can get counted and lead to certain action going forward. Okay. So, that is something which may be needed to be avoided in certain applications. So, for that we can use SR latch, right. So, in the SR latch, the switch is, one is S and another is R, right. So, when it is disengaging from R and connecting to S, so there is a ringing over there. Okay. So, whenever that is happening, so 1 and 0, so the output is becoming 1 because it is getting set. After that, when it is getting S because of the ringing, so it is becoming 0. So, the 0, 0, so previous state is written. Okay. So, there is no issue with that. Is it clear? Similarly, when it is coming to, when it is getting disengaged from S and coming to R, right, it is getting disengaged, no issue, but when it is connecting to R, there is a small vibration. So, R is becoming 1 0 1 0 for some time. So, whenever R becomes 1 for the first place and this is 0, right. So, it will get reset. So, it has got reset. After that, during ringing, this remains 0 and this is 0. So, 0 0 means previous state is written. Okay. So, if you now take output from here, so there will be no effect of bounce. So, effectively you have got a Debounce switch. Okay. Now, we move little bit further. Okay. We look at further use of latch, the basic latch, by introducing an enable input. Okay. So, this is the basic SR latch, which could be made up of NOR or NAND, okay, as the case might be. Okay. So, that is that part we shall see more elaborate circuit later. So, what we are doing here, that we are making S go there through two AND gates like this, okay, which has got a enable input. So, when enable is 0, so these two output are 0. So, that means previous state is retained. Okay. So, this is the case, no change. And when enable is 1, at that time, depending on whatever is the SR value, this 1 1 is forbidden, of course. Okay, the normal action takes place. Is it clear? So, we are not allowing the SR input to affect the final output at any time, at all the time. We are only allowing it when it is enabled. Okay, it is like strobe or the kind of thing that we had used before for multiplexer, demultiplexer, those circuits, if you remember. Okay, so this circuit is active only when, or made to work only when enable is at 1. Okay. So, what is its implication? So, if you look at a timing diagram, right. So, you can see that when enable is at 0, like this place, okay, this place, this place, this place, right. Whatever changes are there, it does not actually, the Q will remain at that value in those cases. So, T1, T2 is the window in which a change can be accommodated. So, S was 1 and R was 0, okay, and Q was 0. So, that makes, if enable was not there, whenever this S was 1 and R was 0, so the Q would have been 1, but the enable comes over here, only here at this point at T1. So, at that time only Q will go to 1, right. Now, T1 to T2, there is no change in S and R. So, Q remains at 1 at T2, at this point T2. After that enable is 0. So, after that R becomes 1 and S becomes 0 at some point of time over here, but that effect does not get reflected in the output Q. Why? Because enable is at low, right. So, again it gets triggered, again it gets the enable signal over here at T3. At that time it finds what is the value of S and R at that time. So, S is 0 and R is 1. Okay. So, that time then it will become reset. So, in between, before the enable was there, if S and R had changed their value, okay, it would not be captured by the final output, right. So, only when the enable is there, whatever is the value of S and R, that gets transmitted and reflected in the final output. So, this is the idea. Okay. So, whenever we want the SR flip flop to work, we put the enable, otherwise we allow the S and R input to settle. If there is any transient and all, we do not want the final output gets changed before S and R is properly settled. So, enable is giving that option period for the inputs to get settled. And this gives rise to what we end with today's discussion is called clocked SR flip flop. Okay. So, the sequential circuit that we shall discuss, it will be actually synchronous sequential circuit. So, most of the sequential circuit are synchronous sequential circuit, where the state change takes place synchronous with a external clock. Okay. So, this external clock actually totally decides how the sequential operation of the different kind of elements inside the circuit. Okay. So, this particular clock would have a waveform something like this, right. So, it goes high and low and all. So, this is one clock cycle, right, and in each clock cycle you are looking for one state change if it is so desired by the input to that particular bistable circuit, in this case this particular SR latch that we have discussed. Okay. And usually latch with a clock is called a flip flop. Okay. But then you will see that in the text it is says latched SR flip flop. So, basically latch type SR flip flop. So, basically they are referring to latch as a flip flop, but in other text generally speaking, presence of clock with flip flop means a presence of a clock, and latch means it is just the last stage of where the memory part is there, where there the value is latched into. Okay. So, that is the way distinction is often made in this particular field. Okay. So, then how this clocked SR flip flop would look like? So, in place of now enable, we are putting the clock. Okay. So, whenever the clock is high, right. So, the input change in the input can be this S and R can be reflected in the output. Okay. So, in this case for SR flip flop, this is the SR latch, right, and this is the AND gate, and this was enable before. So, we have put the clock over there, right. And for NAND based circuit, we remember that this was a NOT gate, right, two input of NAND gate were put together to get S and R, otherwise this was S bar and R bar, right. So, we can now use the other input of the NAND gate to put the clock, okay. And we can see if the clock is 0, this output will be 1 1, these are the forcing input for the NAND gate. So, 1 1 means, right, for a NAND gate 1 1 means previous state will be retained, because this is non-enforcing input for the NAND gate, and only when it is 1. So, this is now non-enforcing. So, based on S and R, the value will be transmitted here, and accordingly the final value will be arrived at. Okay. So, this is the basic SR clocked flip flop circuit, and the symbol for this is this, the one that you see here, and this is also called level triggered flip flop, because we will see edge triggered flip flop in the next class. So, level triggered flip flop means whenever clock is at a particular level, so that time it is allowed to trigger, allowed to change the state. Okay. And if we had put an inverter over here, a NOT gate over there, right, then the change would have been in this phases of the clock when the clock is low, isn't it? So, at that time would have said that this is positive level triggered, high level triggered. So, that would have been negative or low level triggered, okay. And at that time there would have been a bubble sign over here, okay. That is the difference. Is it clear? So, with this we conclude today's class. A bistable circuit has two stable states. To summarize, its value changes only by external trigger. SR latch 0 0 is the input when the previous state is latched into, 1 1 is not allowed, and we can get bounce free switch out of ordinary switches using SR latch. And in gated SR latch or clocked SR latch, there is additional input which enables SR input to go pass through the make changes in the final output. And in synchronous sequential circuit, this clock is very important, and one state change we are looking in every clock cycle synchronized with the clock. Okay. Thank you.